Hey guys, this is the Grid Simulation Group Project for 400D for CSULB's Electrical Senior Design. The group members are England Rasmussen, which is myself the narrator, Abraham Alozi, and Jasmine Torres Molina. Our project is simulating the grid and a microgrid process that can prevent the loss of power during fault conditions. Our project seeks to provide a solution to the constant rolling outages during peak hours on the electrical grid and provide a proof of concept for our project design. The project board consists of DIN rails, relays, MOSFETs, solar array, Arduino controls, center tap transformer, current transformer, a buck converter, battery bank, and other various components. If more information is wanted on the design difficulties, design considerations, and overall information, please see the final report. I will first go over the process flow that our design intends to implement. There are three major parts to this project: the utility controls that provide safe power delivery to two major components, the residential load and the industrial load. Our power supply is coming from a center tapped transformer that supplies two orthogonal 12-volt AC RMS waveforms. We implemented an Arduino to monitor and simulate three different faults. Fault 1 is a critical fault that disrupts power for the residential load and the industrial load. Fault 2 is a fault that occurs only on the residential load, and Fault 3 is a fault that disrupts power to the industrial load. Each fault is also monitored by a current transformer and implements fuses and circuit breakers so no real damage can occur. Our microgrid backup power is only intended on supplying power to the residential load. The project calls for a 5-volt DC source to supply power to the Arduino and to power the battery bank alongside a solar array. Initially, we intended the solar array to charge the batteries alone, but realized we would need many more cells to supply the needed power in a realistic time frame. We implemented another buck converter to solve this issue. Here there are two buck converters. This is the first prototype that was tested on a breadboard and then soldered later. Here is the second prototype that implemented a rectifier circuit on the PCB, higher end capacitors, and an inline fuse. Our residential load is essentially a resistive 12-volt AC rated light bulb. This bulb will get powered from either the inverter during an outage or the utility transformer during normal operation. Here is the solar array that we purchased. It's rated for 6 volts at 300 milliamps. Putting two of them together in parallel increased our output to 600 milliamps, but for our charging setup we would need a lot more power, which is why we implemented a secondary buck converter. The solar array acts as a slow charger for the battery in the event of a power outage, not a full standalone solution. Next we look at the batteries, which are commonly used 18650 cells. We have a 3S 2P setup. This supplies 12.6 volts to the inverter. The controller PCB we are using is a TP4056, which was redesigned to lower the current draw for each cell to prevent an overcurrent on the buck converter supply. We also had to design a charging circuit implementing relays to balance charge each cell individually. I will mention that one downside of this design is that we cannot supply power to the residential load while in charging mode. Now we look at the inverter. The final prototype of our inverter got rid of the 555 timer and put an Arduino in place. This allows us to produce a modified sine wave and fixed a few issues our first inverter had. More information on this can also be found in the report. The output was 12.2 volts RMS, which is slightly lower than the battery potential, which was 12.6. The inverter design is included here. It uses 4 MOSFETs, 4 MOSFET gate drivers, an Arduino, and a buck converter to power the Arduino. This buck converter was an off-the-shelf component in order to save time. Here we have the industrial load, which has a power factor correction circuit attached. Next we see a critical part of the system, the current transformer. These little current transformers are able to sense current and supply an analog output through the use of a burden resistor. A rectification circuit has been attached to the design, and careful calculation of the burden resistor was included as well to prevent damage to the Arduino. Here's the schematic showing the design. Now we can present the entire system working without the microgrid attached. There is a main circuit breaker that we have to turn on. I simulate fault 3 first, which is the industrial load interrupt. We see the motor stop spinning while the residential load stays lit. The relay's red LED indicates this. I want to mention that a MOSFET switching circuit was implemented to energize the relay coils. This was needed as the Arduino cannot supply enough current out of a single pin to energize the relay. Next, I reset the fault, and the motor starts back up. Now I simulate fault 2, the residential load fault. The residential load power is disrupted. I reset the fault again, and then activate the critical fault 1. This kills power for the residential and the industrial loads. Now that I know my program is working and the controls are all intact, I can test the microgrid application with the inverter. I hit fault 3, which turns the motor off as intended. Then I reset the fault. I then hit fault 2, which disrupts the utility power, and the inverter is now supplying power to the residential load. The transfer worked flawlessly, with the only indicator being a flicker of light due to the transfer time. I reset the fault, then test the critical fault, and the inverter does its job again and keeps the residential load on. As a group, we had more ideas for the industrial load, but due to time constraints, it was left fairly simple. The inverter design, buck converter design, current transformer design, and the battery bank design took up most of the allotted time for the project. This project can be easily expanded on as there are lots of room to improve, some of these things being the battery charging design, the inverter size, the inverter efficiency, and the overall wiring. A motor controller could be developed for the industrial load, and another microgrid for the industrial load could also be designed. There was also considerations put in place to provide a visual feedback for the current transformers over current status, but we were not able to complete it alongside everything. Overall, we are happy with the outcome of the project and we have learned a lot. We have successfully completed the main goal of the project and demonstrated that with additional preparation and consideration, a microgrid can operate seamlessly with the electrical grid and supply the much needed power in the event of a fault.